Hello everyone. Let's start with today's lecture. The title of the today's lecture is Representation and Properties of Relation. So here's the outline. As you can see, there are basically the 2 points, representation and the outline. And to make a good understanding of these two informations, we require this prior knowledge. That is, we should have an idea of what is the possible type of representation of a set, that is representation of a set and its representations, and the second is the idea of a relation. Let's start with today's lecture. We'll try to first understand the second point of the outline, that is what are the possible properties of a relation. So suppose that we are given a relation R from a set A to a set B. How this relation is defined? These are the two sets, and now I am making an assumption that of course my A is not equals to phi and B is not equals to phi. Fine, I am assuming they both are not empty. Then this R, this relation, I want to express some of its properties. The very first property, that this R is always a subset of this Cartesian product, and it's by its definition it's natural that it is always a subset. The second property is like I can ask you, it's a kind of a question that we want to answer, that what are the possible number of relations which we can define from this set A to the set B. This is the one assumption which we made. One more information, suppose we have that the number of elements in the set A is P, the number of elements in the set B is Q, then we know that the number of elements in this set is, I asked you to pause the video and answer it yourself first. The answer is number of elements in A times number of elements in B. So P times Q, P. These will be the number of possible elements in the Cartesian product. Now, this is a question that we want to address. You want to answer that what are the possible number of relations which we can define from the set A to set B. Now, if we recall that a relation was a subset of the Cartesian product, and we know that if we are given with a set, then suppose a set has m elements, and if we want to find its possible subsets, then it's given by the power set. How it is defined? By the power set, and the number of elements in the power set is 2 raised to the power number of elements in the original set. So we can apply the similar idea of the power set in context of this relation basically. So if we now try to answer this question, the number of possible relations defined from the set A to the set B will be number of possible subsets of this Cartesian product, and the number of elements in this Cartesian product, if R PQ, then the number of elements, basically the number of relations from this set A to set B are. What is the answer? Now I ask you to pause the video and answer it yourself first. The answer is simple: 2 raised to the power this quantity, 2 raised to the power number of elements in this Cartesian product, which is 2 raised to the power PQ, where my A and B has P and Q elements stacked. Fine. So let's move ahead. So this was one of the main important properties of the relation. Let's take a problem on the property which we have just defined. Suppose that we are given set A, whose elements are suppose say 1, 2, 3, and we are also given a set B, whose elements are C, D. Then we know that the number of elements in this Cartesian product is 3 times 2, that is number of elements in A, set A, times number of elements in the set B, which is given by 6. Now, again the question is that what are, or simply how many relations are possible from set A into set B. Now I ask you to pause the video and answer it yourself. The answer is so simple. The answer is 2 raised to the power number of elements present in the Cartesian product, which is 6. So this is the number of possible relations from the set A to the set B, and this quantity is 64. Fine. So this was about the second point in the outline. Just one last remark to conclude with the second outline is remark. We know that this phi, this empty set, whose notation is this symbol phi, a subset of every set. We know that it's a subset of every set. So in particular, this is also a subset of this Cartesian product, and so in turn it's possible now for this empty set to be a relation. So this is also, this field is a relation from non-empty sets A into set B. So this is also a relation which we want to just clarify. And in order for some capital R that we was calling to be a relation, the necessity condition was there should be some relationship which the elements of the two set must satisfy, and it should be a subset of the Cartesian product. So we can see easily that this empty set is always a subset of any set, so in particular of this Cartesian product, and so is a relation. If I call this remark as one, so one more remark I want to introduce and that is, if I choose my relation from the set A to itself, that is, if my B set is equal to the set A itself, then in this case also my relation, this R is again or is also a relation from set A, is also a relation from set A to itself. These are some very few minor observations that I am making today in the form of properties and the remarks. And now let's move forward to the very first outline, which was representation of a relation. Now let's try to quickly understand the first outline, that is the representation of a relation. So there are two possible approaches through which we can represent a relation. Either it is algebraic approach, algebraically, or the second is a visual approach. For the second one, we have something called arrow diagram, which we have already explained in the previous lectures. You can refer to them, arrow diagram. So this was one way to represent a relation visually. We want to visualize it, and algebraically, this is a convention. Like there are again the old two approaches. The first one is the roster form, which we have often used while representing our sets in the very first series of set theory, and the second is set builder. depending upon the kind of relation, the number of ordered pair it has, you have to choose accordingly the which form is better for you. If there is some property which all the elements of the ordered pair satisfy, all the ordered pairs satisfy, then of course that middle form is better. And if you want to list explicitly the ordered pairs, and if they are very less in the number, you can count them easily. If they are very less, then of course this is a better option to go with. We have covered both the outlines, and now we can conclude the video and with some important information that in the coming videos we'll be discussing what are the possible types of relations, and finally after explaining them we'll be moving forward into the chapter with functions. So that is the most fundamental concept which will be required. So thank you so much for attending, and do like and share the video, and also about our initiative, and do subscribe our channel. Thank you so much.